Okay.
Chat.
Alright. So yeah, we are at here.
1 minute ya.
At line number 9.
Um,
Can you see my screen?
no, no, no.
Oh, you can't. Can you see my screen?
Yes. Oh,
Yes.
why can't I see your screen? Yeah. 1 minute. Okay, now I can see it.
Alright, so we are at line script number 9, upstream of methanol tower.
Okay, 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 okay. Okay. So good. Okay. So before, I think last week we discussed that we're going to spend some time on this distillation column. Okay. So before we go into that, yeah. So I will just share my screen so that we can see how we should model this. Share screen. Start sharing. Do you see anything? Oh.
Yes.
Okay. Okay. Sorry. So I think as mentioned, so we are now here stream 9, yeah. So this stream 9, it consists of the unreacted methanol, and then the DME as the product, and also the water as the byproduct. So we can see the we can see the stream conditions over here roughly. So temperature is about 90 degrees C, 10 bar of pressure, and then we have some vapor, and then we have the DME, and then water, and then the remaining of the methanol. And basically what we would like to do is then we are going to separate the DME to the top, and then we will then have it at this, the distillate stream, and send it to the storage, and then the unreacted methanol and water, they will go down to the next unit. So we'll take a step back. I don't know if you still remember how to design a distillation column, Aisha and the others.
Yeah.
So okay, so let's assume that we all don't know, yeah. So the first thing that we need to do is then if we want to separate a component, sorry, want to separate one component from the others, like in this case, we have like 3 components, yeah. We have 3 components. So what we normally do in designing a separation system, this separation system is based on the properties that make them different. So one of the most famous properties that we normally use that differentiate the components is the boiling point, so the boiling temperature. So if we see if we don't know, for example, if we are doing with different chemicals, for example, so we can Google the dimethyl ether, and then methanol, and then water. So opening my Google. So we can either Google it and then find it in the Wikipedia as the generic information, or we can also find in NIST. I don't know if any of you have heard anything about NIST.
NIST?
NIST, NIST. A minute, yeah, I will show you. one command item, which one's faster? This one. So for example, the methyl, simple way is to Google this and then go to Wikipedia and then open, and then NIST is somewhere. Normally if you could see this in this public cam and CVI, that's also one, and then NIST is you could see it in here, NIST. So many of these, I think the process simulation software, yeah, either ISIS plus SVN plus or whatever. So they take the data from this NIST chemistry webbook. So NIST stands for National Institute of Standards and Technology from US. So they have, for example, if you want to see the gas phase data, so you can just click, and then it gives us this gas phase data. So the enthalpy of the gas, the enthalpy of formation of the gas, and then the combustions of the gas, and then we can see the Cp as a functions of temperature, and then we have the Cp as a functions of it's also a function of temperature. So at different so these are then all the data that they take. So and then you could also see, if you want to say for example, phase change data. So they have all of these boiling temperature, triple points, critical points, and so on and so forth. Also the evaporated energy. Also, we could also see from Wikipedia as the first step. Yeah. So we can see, because NIST is very detailed. So we need to know first what we would like to know. Then we can go to NIST. But then the Wikipedia, you can use it as starting point, and then we can see for example, this is the metal ether 46, then the molar mass, and then it has density of for example in here about 25, it's minus 25, I don't know, minus 25, 0 degrees C gas. It's so we don't have the density we don't have the density of the metal ether at the room temperature from the Wikipedia, but I think we can have it here, condensed phase. So condensed phase, they don't have it as well. If you go to maybe this guy, PubChem. So these are like several websites that I normally go to. Where is that name? Chemical. Okay. So now here, no, they don't give any density as well. Safety, no, nothing. The other one is then ChemSpider. ChemSpider, yeah, this one, ChemSpider. Now it gives the density. Oh, this was the ethyl ether. And then we can see, we can click on the properties and then the density, and then it gives us this yeah, there are many experiments, and then we need to just click on it what it means. And then this one is then yeah, it's gram per milliliter, it's about 661 kilogram per meter cubic roughly. Yeah, it's about this number. And then this is then also and then we can see also the melting point of the metal ether, the boiling point of the metal ether, which is minus 24 degrees C. So that means we know at room temperature, it's already in the gas phase. It's already in the gas phase. Yeah, as it mentions over here, colorless gas. So that metal is already at the gas phase, and then we know that water is boiling at 100 degrees C. And then how about methanol? So methanol is boiling at which temperature? So you can see methanol is boiling at 64 degrees C. So if we then list them or sort these three components in the order of increasing of the boiling temperature, so we would put dimethyl ether at the top, and then the dimethyl ether at the top. So it's minus 64 degrees C, and then methanol 64 degrees C, and then water at 100 degrees C. So this list is already I don't know, coincidentally it is already based on the ascending order of the boiling point. So in this case we can then know, so if I have the metal ether as the lightest component, then I know for the first column I need to remove the dimethyl ether in the top. Yeah, because dimethyl ether is the lightest component, and then we separate them, dimethyl ether at the top, and then the wastewater, and then the water, and then the unreacted methanol goes to the bottom. So that is then our first information on how much, what to split, and then we will see later on how we can then yeah, define how much to split. Yeah. So the for the second question, so how much we have to split, we normally, because this is then our main product. Yeah, this is our main product. So this main product, normally if you go to the like a supplier or something, they will tell us how much is then the purity required by this DME. Yeah, that's number one. So we have to have then the purity constraints. And then, for example, this is then stream number 10, and then if we can see here, so 129.1 is then the amount of dimethyl ether, and then we have like some amount of methanol, and then you can see, yeah, we can calculate this roughly. So 129.1 divided by 129.7, so we have 99.5% mole. Yeah, so we are going to produce 99.5% mole of dimethyl ether in the top. So we know that we are going to produce the purity of this dimethyl ether that we're going to make is 99.5. Okay, so again, step number one, we identify what the stream is that we are going to separate, and then we list them based on the yeah, the properties that we want to utilize. In this case, we are going to utilize the boiling point difference. So we list them down based on the ascending order of the boiling point difference. So in this case, we will have like dimethyl ether in the top, and then the methanol, and then water. So we know that we are going to separate dimethyl ether in the top. So, and then also we need to know the purity, which in this case it is given to us. It's 99.5% of DME in the top. And then the next question is then how much. So how much is then because this is then our product. Obviously, we would like to maximize the product, right? So whatever DME that is coming in this stream, yeah, in this feed stream, stream number 9, we want to recover them as much as possible, right? So if stream number 1, the DME is 130, so in this case we are going to recover 129.1. So we can see, 129.1 divided by 130.5 is about 99%. So 99% of DME we are going to recover. So remember these numbers, yeah? So we are going to recover 99% of DME coming from stream 9, and then the purity of that DME itself is about 99.5%. So these two parameters are our keys to design or to simulate this distillation column. So we are lucky here in this case. If you have any question, just ask. Yeah, we are lucky here in this case that we have the column designed for us already. So maybe in the next sessions we will then discuss on how to design a distillation column. But in this case, we'll finish this all simulations, and then we go on equipment to equipment basis. So we are going to simulate 22 stages, and in this case, the liquid from the 22nd stages will then go down to this collector, and then the liquid will then passing through this reboiler and comes back as a two-phase flow normally. So the vapor goes up and then the liquid goes down. So this liquid is going down over here, that liquid is going down over there. So we have two different concentrations of liquid, but they are collected in the same part of the column. Hence, we don't consider this as a separation unit. Yeah. So we only consider tray 1 until tray 22 as the separation unit. This one as well, if we see at stream number 10, we see that there is no vapor. Vapor fraction is 0. There is no vapor, and then we know that We don't know yet. Yeah, we don't know yet. We do know that at atmospheric pressure, the boiling point of DME is -64. But then in this case, we are all going to operate that at 11 bar. So if we look at this data, we are going to make a liquid DME. Yeah, there is one source of information. The other source of information is that you can then plot the phase diagram. So we have discussed on the phase diagram before. So you can plot the phase diagram of DME so that you can see if I would like to make DME in liquid, what is then the operating pressure or the operating conditions that I need to have to make DME in liquid, for example. So let's begin. So in this case, if we want to recover this as a liquid, that means the whole stream here, because this whole stream, what comes out of the top part of the pre-boiler, it has to be in a vapor phase, right? And then it is going to be condensed, and then the DME or the condensed part goes pumped, and then it goes to the stream 10. So we know that this is then a liquid line, yeah. So we know that we are going to condense this from vapor to full liquid. So let's do that. I think you can share your screen, Aisha. Any questions so far? No? Don't see any question. Okay. Where's the palette? Palette. So we need to add the what was it again? So we go to the yeah, separator, and then distillation column. Not that one. That is a vessel.
Is it?
No. Not that one. That's a vessel. So we go.
Oh, this one.
That one.
With
Yeah.
reboiler and
Yeah.
alright.
Okay, and then you can make the connection. One minute, yeah, because you put already like stream 9. Yeah, okay, stream 9. So now number of stages is 22, right? So you can just type 22. It looks because it looks different to me, but anyhow. And then okay, so number of stages is 22, and then we know from the book, yeah, let me open that book again. So the stream 9 enters at stage 12. Yeah, okay, and then we say that we are going to see, if you see this on the condenser part, yeah, you can rename it. Yeah, you can rename the column if you want. Rename the column. This is I think this is T201. Yeah, and then the condenser, we know that already that we are going to fully condense this. So in here we have total, partial, and full reflux. So in this case we have to select total, because it's going to be total condenser. So you can see, you can see one step at a time. So you can see from the top of the column, it goes to the condenser, and then it goes to this vessel, so that reflux drum. And then when you take total, in the beginning there was a line, yeah, there was a line going out of the if you take partial again, take partial. Yeah. So if you take partial, there is a line, a vapor line coming from that reflux vessel. Yeah. So there will be like a vapor, and then there will be like a liquid. So there are two streams, vapor and liquid, because we are partially condensed. But if we take on total, so that vapor is no longer there, because we are going to condense all of the vapor. Yeah. So so in this case, we select total condenser, and then now you can then, yeah, make the necessary streams, yeah, the condenser stream, liquid outlet stream, reboiler stream, and then the bottom liquid outlet. Yeah.
So how do we know which stage should we set for our meter?
We will discuss that later, yeah. Okay, so that is one, and then don't close, so because this gives this, because you can see, distillation column input export, that's the name of this window. So so in this window there are five pages. If you see, go down, next to that cancel, you can see page 1 out of 5. So we are still in the page 1, so you can click next. In this reboiler configurations, if we know what the reboiler configuration is, which I think in our case there will be like the it's not there, yeah, because what we have, if we see roughly, it is also not shown clearly in the PFD. But what I guess what we are having is that liquid from this, from stage 22 goes straight to the bottom of the column, and then it then goes to the reboiler, and then reboiled, and then goes back to the column. So in our case we don't have such configuration, but I think we have the B, that circulation without baffle, so it's more or less the same. But yeah, it doesn't really matter in this steady state situation anyhow. So you can see, you can see the liquid coming from the stage 22, for example. It's in the black arrow pointing downwards, so liquid going down, and then some of it is going to be passed through the exchanger, getting two-phase flow, and then liquid is then mixed with the liquid coming from the top tray. And then click next. Now condenser pressure. So in this case, we need to specify the condenser pressure. So if we see on the book, yeah, in the book it says that the pressure is about 10.3 bar at the top of the column. So we can use that. So that one's 10.3 bar. Yeah,
Right.
and then in this case we can just yeah, if you want like to put, because stream 11 is then at the bottom of the column, and then stream 11 is 10.5, so you could also put 10.5 at the last stage pressure. 10.5 bar. Yeah, and then the pressure. No, it's it will be calculated accordingly. So because we know there will be like 22 stages, and then top stages is the top stage is going to be operating at 10.3, bottom stage is operating at 10.5. So 0.2 bar is then the pressure drop from the top to the bottom. So it will then be calculated evenly.
Alright.
Click next. This one is optional. You can just skip it. Next. And then this one, you can put liquid rate or reflux ratio, but I'm not going to do that on this page. So we can just done, click done. Yeah, this one. This is the important. Can we make it a bit smaller? Yeah, like that. This is too small because I don't like to scroll down. Exactly. Very good. So so in this design page, you can go to monitor. Design still
Okay.
this one, monitor. So now this monitor is the most important page that we need to until now. Yeah, I mean at this point in time, this then typically this is going to be the most important page that we're going to see. So so the specifications, you can see the bottom as the specifications here. We have reflux ratio, distillate rate, reflux rate, bottom product rate, or whatever. And then you can see as well on the right, there's they take 3 items as active, estimate, and current, right? So 3 items. So reflux ratio, it makes it active. Distillate rate is also active, and then the bottom split 11 active. I don't know what that is, but in any case, if we tick 3, that means as active. In this case, you can see also the degrees of freedom. It's 0. Yeah. In this case, that means we have fulfilled the necessary information to get the simulation run, but it's just that we don't specify these three numbers. Okay. Now I think I know what this bottom split is, because in the previous page we see we select the reboiler setup in the middle, right? So do you remember that one?
Let's see.
I don't know how we go back to that page. Yeah, maybe we can go to
Is it this one?
no, not this one. Do you remember that we selected one of the reboiler type?
Yeah.
I think because we have selected that the option in the middle, so we have a split. So there will be like one stream goes as the bottom product, the other stream goes to the reboiler. So that is then this split. So in this case, I think because we don't have the information, yeah, we don't have the information of how much the split is going to be. So I think I'm thinking that if we can go back to that page and then we just select the default reboiler setup, simply because we don't have that information. Yeah. Let me check. Yeah, where is that thing?
We can.
I can go to parameters maybe. No, yeah. Internals is normally the column only. No. I don't know how to go back as well. Yeah. So in this.
Is it this one here? Column environment.
Will be in the detail, but I'm not really sure. It's the same. It's going to be the same as in the internal.
Ah, okay.
That column environment. Well, Reflux rates. I'm not really sure. Yeah. Well, yeah, there's one thing. We use the hardcore. We just delete it and delete this and then make a new column.
Sure.
That's also better. And that is 12 stages.
So then this is E 044. Opening the cuts.
Yeah, Shafiq has made a print screen on these three different types of reboiler that is available in IC. So we have selected the middle one. Yeah, while waiting for Aisha, so you can see on the shared picture by Shafiq that we have selected the circulation without baffle in the middle. So in this case, apparently we have to have a data on how much we are going to split, yeah, to the product and also to the reboiler. So well, we can make quick and dirty assumption, but let that be the next task. So just select the ones through.
Alright. Regular high-sensitivity boiler.
Yeah, and then click next. And then this condenser is 10.3 bar. Below is 10.5. Yeah, exactly. Next. Next. It's also done. Yeah. And then we go to the monitor. So you can see, now it's by default it is now taking the reflux ratio and then this flow rate. These two are ticked as active, and then the degrees of freedom is also shown as 0. So that means we are yeah, that's only like 2 degrees of freedom to operate this column or to do the calculations. Yeah, in the previous units we had 3. Now we delete that, and then now we have 2 only. So which is easier at this point in time. As an introduction, it will be easier to manage. So typically what we have in the plant is that we are controlling the reflux rate, and then the that one we control, and also the temperature in the reboiler. That's what we control, not typically. Yeah. But in the simulation you could do that, but now let's do it the easier one. Yeah. So the easier one, since we know already the what we need to separate, DME 99.5% purity, and also 99% of DME coming, we are going to 99.9, right? I think 99.9 of DME coming, we are going to recover that. So in this case, you can click add spec. No, in the same monitor, and then so you can down, you can add spec. So in this case, we will do like a column component recovery, because we are going to recovery. We are going to recover the component. Yeah, we're going to recover the component. Hence, we need to search for component recovery spec. So rename it recovery DME, for example, so that we know. Just type or double click. Yeah. And then it's going to be on which stream that we want to have the DME 99.9%. The top of the stream, the column, and then the flow basis is molar, right? Because we just calculated that in molar. You could do that in mass, up to you. And then what do you want to recover? Click and then DME, yes. And then how much is that? That's the spec value. The spec value there, yeah. So we can say that we want to recover 99%, 0.99 in this case. 0.99. You have to write it 0.99, Aisha.
99.99.
0.99, 0. So it has to be from 0 to 1. Yeah, that one. Yeah, very good. And then close this. So you can see, right? You can see now the DME recovery is there. So you have specified the value to be 0.99, and then it is not active currently, but okay. At least now we know we are going to have this DME recovery as a control. Yeah. And then you could also do click another one, add spec, because we know that we want to have the DME purity. So DME purity is then what do you think? Yeah, component fraction. Add spec, and then you can rename it like DME purity. And then stage is the condenser, right? At the top. Mole fractions as well, and then phase is liquid. And then this is 0.995, exactly. And then the component is DME. Yeah, close. Okay.
Right.
So so now we need to make this DME recovery and then DME purity as the active controller, so to say. So we just untick that reflux ratio and distillate rate. So you can see, 1 minute before you tick this too. Untick. Anyhow. Fine.
Hold on, it's
Yeah, it's already solving. So we can see, I just want to show you. So if you untick one, that means you only tick one. So you have a degrees of freedom is 1. So that means we are missing one active control in this case. So so that's why we have to tick 2, or we have to put 2 active specifications. So that it will then use ISIS will then use these informations, the specified values that we input, to be the yeah, to solve the how do you call it, to solve the calculations. So you can just tick again the DME recovery. You can see the specified value is the value that we want, and then the current value is then the current value that how now HYSYS is doing. So you can see the DME recovery is about 100% and the current value, and we said that we want only to have 99%, and then the purity of DME is also like 100%, while we want to have it like 99.5. So it gives us already the best scenario that we can think of. Very pure DME, 100% DME recovered, but we want to have it like in the mediocre range. Yeah. So now I am suspicious on the stream 9, because in the mass balance we should have methanol as well, right? The unreacted methanol, because if we see, it doesn't converge. So in this case, because we remember, yeah, the 1 minute, yeah, 99.9 in this case, and then DME purity, and then you can see the reflux ratio is 3, and then distillate rate is 140.7 kilomole per hour. So we would like to have the distillate rate, because it is a stream 10, that distillate rate is 129.7. That's what we would like to have. Yeah. And then we don't know what the reflux ratio is. Okay. So hence this is what I typically do in the beginning. So I control the recovery and the purity, but since we it doesn't give us the answer, another way to solve this, yeah, very quickly, is that since we know already what we would like to have, the distillate rate, so we can then type it 1 minute. So can you go back to your stream number 9, because your stream number 9 can be different from the stream number 9 is what we have. Go to composition. So DME is 0.4284. This is in mole, yeah. So 0.4284. So if you multiply this with the flow rate of the stream 9, how much is that? 0.4284 times 328.5. It's a 140. Yeah, so 140.7. Right, 140.7. So you go back to that design and then go to the monitor. See, if we recover the whole DME, yeah, like in this case, the distillate rate is that 140.7, exactly the same as that 100% of DME recovery. To get that, so so to match with this, to match with the data that we have, yeah, so we could then untick this DME recovery and then key in that distillate rate. So in our case, for example, if we would like to have 99% recovery, so that means 99% of this 140.7 is the one that we have to take in the as the flow rate of DME in the top. Can you follow? Yeah, if you cannot follow, let me know. Because let me calculate this for you, yeah. So 140.7 times, we would like to recover only 99%. So it's a 139.3 is the flow rate of the DME, yeah, 100%. Okay, but we need to make it 99%, 99.5% of DME. Yeah, so that means if DME is 139.3, can you follow? Because I'm afraid that you cannot follow. So if this 139.3 is then the pure DME, but we would like to have 99.5% DME. So that means we need to add methanol to it. How much is then we are going to add is then 139.3 divided by 0.995. 139.3 divided by 0.995, and 140 is that, and that is then the total amount of distillate that we're going to draw.
Alright.
Can you follow?
Yeah.
Let me know. Yeah, so I repeat, yeah, this 140 consists of DME 99.5% and then 5% methanol, supposedly.
Alright. Yeah.
Yeah, and then we only recover 99% of DME for the sake of matching the stream data. Yeah, this is for the sake of that. So I'll close that, and then take wait a minute. Okay. Quick stop, and then untick that DME purity. Yeah, so now reflux ratio. So let's play by the book, because the default is also reflux ratio and distillate rate. So typically, yeah, if you see like typically in the book or in experience as well, it's the reflux ratio is about 1.2 to 1.4 typical numbers. So in this case, you could put like 1.4 in the specified value. Yeah, up to you. And then make it active, and then we'll see what happens.
Convert.
Yeah, it converge, and then you can see the DME recovery is the 99.5%, the current value, and then the DME purity is 100%. So we are recovering the 100% of DME in this case. We don't manage to get methanol in the top, but okay. I want you to add also this reflux rate and bottoms product rate. I think we can delete them. Right click on that, yeah. If you can right click, nothing, yeah. No. If you double click on that reflux rate, yeah. And then the bottom rate as well, delete. Okay, now I want you to add reboiler duty and then also condenser duty. Column duty. Look at column duty. Column duty. Column duty. Duty. Yeah. And then so rename it as reboiler duty, for example. And then energy stream is then which one is reboiler? 204.
Yeah, 204.
Not 205, yeah.
Nope.
Okay, and then you close this. And then you can see the reboiler is then 5.8 kilojoule per hour. 5.8 million kilojoule per hour. And then add the condenser. Column duty. And then rename condenser duty. And then close. Yeah, so 6 million kilojoule per hour. Okay, so in this case, I don't know, do you want to have like a methanol in your product stream or no?
I think it would be much more, I don't know.
Yeah, you could put that if you increase this to 141, increase the distillate rate by 141. And then you can, one minute, before you do this, escape. Okay, so memorize this number, yeah? The reboiler duty and then condenser duty. I don't know how you memorize it, but you have to memorize it. And then yeah, before we okay, and then now try to increase the distillate rate. Very good, Shafiq. Increase the distillate rate to 141, for example.
I don't think it will be converted.
This is just for the sake of getting that methanol up in the top. Doesn't seem to be that methanol wants to go up. I don't know why.
Can we try case study on this?
Well, you can, yeah, Shafiq. You can do so. And then you can see, you can then vary. For example, like what we did last time, you vary the reflux ratio, and then see how much is then the results, and or you vary as well distillate rate, or you vary both. So it's not converge. So put it back to 140. In this case, you could also play with the reflux ratio. Say, for example, you reduce the reflux ratio to 1.2. Can we still get what we want? Yeah, we can still get what we want. And then you can see the condenser duty and then the reboil duty has decreased by a number. Yeah. So because if we reduce the reflux ratio, that means we are reducing the amount of liquid back into the column. And then you can also reduce the reflux ratio, reduce it to 1, for example, or 1.1, up to you.
We will still be getting this thing.
Yeah, we are still getting the perfect separation. Okay, now 1020. So you could play around, yeah. I mean, I hope that you are playing around. You play around on this this column, and we can and we'll discuss next week. Now I want to show you. Can I don't know if I can get control. Yeah. Can I? Is there any control? No, yeah. Anyhow,
Control.
mouse control. No, yeah. So if you can, anyhow, you can see temperature versus tray position from the top. Yeah, temperature versus the tray position. That graph. So in that graph, we have the 22 stages, and then plus the reboiler and condenser. That makes it by default. ICES put this as the stage. Anyhow, so it's going to be like 24 if you see this roughly, right? 23. Sorry, 23. So the reboiler is then one stage. So we and then y-axis is then the temperature. So we see here, what we are seeing here is then that the temperature profile along the stages. Yeah, you can see. In this case, I think when you dig more information on this column, typically it will be like efficiency will be by default it's going to be 1 or 100%, but we will see that later. And in this case, we can see in separation, if you can still recall, especially in this vapor liquid equilibrium, this we know that the separation happens because there is a temperature difference. Yeah, and then you can see here in many of these stages the temperature doesn't change at all. So for example, you can see from stage 0 or stage 1 until stage 10 or 9, the temperature barely change. Can you see that? Yeah, so the temperature is constant from stage number 1 until stage number 10 or 9. So in this case, you can see later on, you can see that there is no separation happening here in these 9 stages. And also, you can see that. And then also from stage number 1, 2, 3, 10, 11, 12, 13. So stage number 13, 12, 13 until 16, 17, there's also barely any separation. Yeah. and then we know that we are giving the feed at tray number 12. Hence, you see that jump, right? Okay. I think we can go also to the performance. Can go to performance tab. Column profiles on the left. Yeah, and then let me see, because I would like to see feed that plots. Can you go to the plots? Plots on the left as well. Composition, and then view graph. Make it bigger. Nah. Can we add? I don't know if we can add temperature, but anyhow, you can see, now we just mentioned that the temperature from stage 1 until stage 9 or 10, they are constant, and then here you can see the concentration of methanol, which is the light, the blue, and then concentration of DME, red, and also the water. They are all constant in stage number 1 until stage number 9 or 10, right? So it confirms that there is no separation, right? So that means this stage number 1 until number 9, they're not doing anything basically. So practically you can remove this stage. Yeah. So that's one item. And then you can also see stage number 13, 14, 15, 16. It's also like there's nothing change in the terms of temperature. And then we can see it also in the compositions. There's nothing changed. So basically we can also cut these 3 stages or 4 stages from these sections. So we can barely now we can see we can cut 9 stages from the above the feed location. The feed location is stage number 12. So we can remove 9 stages in the top, and then we can also remove 1, 2, 3, 4, roughly 4 stages below the feed stage. Yeah. So we are going to cut this column from 22 stages into 9 plus 4, 13. So 22 minus 13 is about, I don't know, how much is that? 9 stages only. Yeah. So these are what you can do as well in the practice, provided that you have that we have how do you call it, the correct performance of the tray. But in this ideal case, we put the ideal efficiency of 100% per each tray. So this is what we get. Yeah. But basically, you can do what I just said. So later on, I think you could cut this. Yeah. If I think you can do this later on, and then show me next week. So you can cut these 9 stages in the top, and then 3 or 4 stages in the below feed stage, and then you can see what happens as well. So you could do that. One more thing to answer that Shafiq's questions on the what was it again, Shafiq? The feed location. Yeah, very good. Feed locations. In this case, how do we know if we are using the correct feed locations? So this the correct way to do this, the correct way to do this is then we check the feed concentration. Can you go back to that concentration profile again, Aisha? Performance, plots. Yeah. So and then our feed concentration of stream number 9. I don't remember, but then can you open, or can someone open? Can you make it a little bit smaller, like half of the screen, and then let it be like that, and then open that stream number 9. Very good. Or maybe worksheet. Yeah, very good. So compositions. Yeah. So we have the DME 0.4, water 0.4, and then methanol 0.1. So the best location to put the feed is then the feed that has the closest concentrations as in the feed. The stages. Sorry, the stages that have the closest concentrations as in the feed. So you can see here, DME is 0.4 something something, and then the water is about 0.4 something, and then the 0.2. So this stage number 12 seems to be like the okay stage for the time being. Yeah. So that's how to see this number in one glance. The second way is that I think Shafiq mentioned that you can do case study. You can do case study, and then vary the the stage number. Vary the stage number, and then plot the reboiler and then the condenser duty. Can you follow? Yeah. You vary the stage number using the case study, and then or maybe you want to do it, yeah, for the last 2 minutes. So, and then we vary the stage number, and then the stage number, the feed location, and then we check how much is then the reboiler and then the condenser duties.
But what are we trying to look at the pattern of the reboiler duty and condenser duty?
So basically, these duties good. So basically, if you are to run these columns, you want to, because these duties, the reboiler, for example, they will be using steam, yeah, like a hot medium. So this steam or hot oil or whatever, it comes with a price, so we have to pay for them. The same goes with the condenser, even though it's much cheaper because it's going to be cooled in this case with cooling water anyway. So it's going to be a cheaper cost. But then the question is then we would like to see at which stage is then the amount of duty is the minimum. Because if we can find the minimum amount of duty, that means we just need to pay the minimum amount of money to get the same separation performance. Yeah. So I think that can be the homework. Make the case study, and then if you can't, I think you can do it. But if you can't, anyhow, we'll discuss next week. And then also another homework is then try to cut the column. Yeah, so we can just remove the column. Remove the stages that don't have any difference in temperature. And then do these case studies.
Yeah.
Okay. Any questions? No.
I'm good.
Yeah. If there is no questions, then I will see you next week with these 2 items done. Or at least we have something to discuss next week, so you don't come blank. Okay. So see you next week. Have a nice weekend. Save this file, yeah, Aisha.
Yeah, I did. I already.
Thanks, yeah, Aisha.
Thank you.
Yeah.
Alright.
So have a nice weekend. Bye bye.